All right, in chapter 8, part 4, we're going to go over a few more types of reactions. And to start off, we're going to go with catalytic hydrogenation. We're going to be adding hydrogen to both sides of the double bond. So whatever is already attached, of course, will still be there, but we are going to add an H to both sides. Now, what does this require? Well, H2. But H2 alone will not react, or at least not react quick enough to be useful with a double bond. So you have to have a catalyst. Now, I'm just going to write catalyst here because the catalysts that I want you to know are either palladium or platinum or nickel. All right, those are going to be the solid metal catalysts that you should be familiar with. One that you might also see pop up in practice problems is it's going to look like this, or it might even look like this. And that just means palladium on carbon, and it's just a way that palladium is sold. I think maybe it makes it a little bit more stable, but the point is it's still palladium. It's still that metal catalyst. And we don't have to worry about regiochemistry, right? There's not going to be mark or anti-mark because you're adding the same thing to both sides. But what you do want to know is the stereochemistry. This is a syn addition. And this is an interesting mechanism because we have our first heterogeneous material. So this is a heterogeneous catalyst. Because everything is in solution, the alkene is in solution, the H2 is in solution, but the catalyst is a solid metal. And that is going to hopefully give us a visual for why this syn addition occurs. So this becomes particularly important in an example like what we have here, where we have this di-substituted cyclohexene ring where there is a very significant difference in whether the H's add to the same side or to opposite sides, right? It's going to wind up pushing the two groups, right, the ethyl and the methyl, either both wedge or both dash. And why does this happen? Well, with the catalyst, we are going to see a very good visual of why. Now, catalysts work in a couple of ways here, right? They help the reaction go faster. They are not consumed by the reaction. And you've always kind of heard this, right? Catalysts help to speed up a reaction. But how do they do that? Well, it changes the mechanism, right? It makes the bonds break and form in a different order or with different intermediates. And sometimes with more steps, like you see here with a catalyst, the red line has multiple transition states, 2 intermediates, but each one of those has a much, much lower activation energy. So more molecules will have enough energy to get over that activation energy barrier and will in turn make this reaction go faster. So in this case, the mechanism is drawn a little differently than what we've been seeing before because we have this solid state metal here. These dark gray spheres represent our palladium or our platinum or our nickel. And what happens is when you pass the H2 over that metal surface, it absorbs onto the surface of the metal, right? So you see all these little individual hydrogen atoms. The H bond has broken and it has formed a bond to the metal. Then your double bond comes in and you get an attraction, right? That pi bond starts to break and it kind of happens all together. The pi bond, you see it kind of adhering over to the metal on one side, but it picks up a hydrogen on the other. And then this bond, right, this carbon metal bond shifts and picks up another hydrogen. So you can think of it as this flat surface of this double bond comes in and picks up a hydrogen off the surface. So it has to pick it up on the same side. It won't pick one hydrogen up, flip over, and then pick the second one up, right? It picks them both up when it's facing in one direction. And so you get that syn addition, right? So for each new reaction you're learning, you have to keep track of a few different things, right? You're keeping track of the reagents itself. You have to memorize those. You are keeping track of regio concerns, if it's mark or anti-mark, if that makes sense. And you have to keep track of the stereochemistry, if that is applicable. And in this case, it is a syn addition. And it's important for predicting the right products, for knowing that you are going to get a product where both of these methyl groups are on the same side, right? Either wedged or dashed. In this particular product, it's a meso, so they aren't enantiomers of each other. They're just the same. Whereas in this example, right, there's two chiral centers, but you don't have that internal plane of symmetry. So you actually do make two enantiomeric products. Now, depending on the practice set, you may just see one or the other, or sometimes what you'll see is one answer plus En. Instead of drawing out both enantiomers, the plus En just means they could have either added from the front or the back. There are other catalysts, so we are only interested in the heterogeneous catalysts. I am not going to test you over the other homogeneous catalysts, but there are other metal catalysts that can be used to do the same thing. We're going to stick with our platinum, palladium, and nickel. I won't ask you anything about Wilkinson's catalyst, and I will stick to asking about syn addition using cyclic structures. So you won't have to worry about where the wedges and the dashes on an open chain wind up. There are also chiral catalysts that can help you. If you could make, an R product or an S product, it can help you be more selective. But that's just a fun thing to know. We are not going to cover asymmetric hydrogenation. So you do not have to spend time working on that. Or the Nuyori synthesis. This is the same idea. It's in that asymmetric hydrogenation. A lot of cool different catalysts out there in the world. I want you to focus on these. Palladium, platinum, nickel. Be prepared for palladium on carbon. Now, another reaction that doesn't, you don't have to think about the regiochemistry is halogenation. Now, we've done hydrohalogenation where we have added HX, but now we're going to be adding X2. So we're going to be taking a carbon-carbon double bond, and this usually works with bromine or chlorine best, but you are going to add a halogen to each side, right? So there's not more or less substituted. A halogen goes on each side. And this one is anti-addition. So this is our first example of a reaction where the stereochemistry is not syn, it's anti. So instead of going to the same side, the halogens are going to go to opposite sides. Now, this is a single bond, so it can rotate, but if it confuses you, you can always put the X down here so it's more obvious, right? They go to opposite sides of that double bond. So it is stereoselective. Now, you'll notice here, and you see this sometimes, bromine and chlorine are often really good halogens for organic reactions. Fluorine is the special guy, and we have to do other things if we want to put a fluorine in. In this case, it reacts way too quickly, and it's too violent to be useful. Iodine is the opposite problem. It's way too slow. So we really stick to chlorine and bromine here. And notice in these predicted products, we get a bromine on either side. So you get the trans product. And so again, you could show both of them, or you could see this plus En, which just means plus enantiomer. Now we are going to look at the mechanism to help us understand why we get that anti-addition mechanism. So the very first thing is your double bond, and I'm just going to use the little cyclopentene, is going to react with the bromine. Now you might think, well, Okay, I can see how a double bond is a good nucleophile. There's a lot of electron density in that carbon-carbon double bond. But Br2 is not an electrophile. That is a nonpolar bond. And that's correct. That is a nonpolar bond. But what kind of intermolecular forces do you have even with covalent nonpolar compounds? You have London forces or dispersion forces, right? So think about where those occur from. You still, in a bromine molecule, right, have this cloud of electron density. And at any given time, you might have more electrons on one side than on the other, which would give a little partial negative, partial positive, right? A temporary dipole. And as a nucleophile approaches, as that electron density from the double bond approaches, the electrons in the double bond repel the electrons in the bromine molecule and induce a dipole. And so you do get a nucleophilic attack on one of the bromines in the Br2 molecule because of that temporary induced dipole moment. And it does cause this bond to break. Now, I'm not going to draw exactly what's on this slide because we don't actually make a carbocation. And we know this because there's no rearrangements in these reactions. What actually occurs, instead of having this carbocation here, you have just added this bromine, which has a ton of electron density on it, right? It's got 3 lone pairs. And so one of those lone pairs will be attracted to the carbon that is losing its the pi bond electrons. So in reality, we actually make, hold on, I'm going to skip over this because the way they're showing it here acts like we have a partial positive. And then the bromide ion could attack either side, and that doesn't happen. So there's no rearrangements, and it is stereoselective. You only get anti-product. So this doesn't actually make sense as a mechanistic intermediate. What we actually get is this cool little triangular intermediate. It's called a halonium ion, or in this case, bromonium ion if we're using bromine. And so you wind up making 2 bonds to that bromine ion. This keeps it from rearranging. You have a plus charge on the bromine. All of the carbons are happy, and then you have a bromide ion. Now, that little ring has to be on one side of the ring. They either have to both be wedged or both be dashed. You could try to make a little 3-membered ring where one's going towards you, one going away with your models. You can't do it. The geometry is just impossible. So they either both need to be wedged or they both need to be dashed. And so what happens is an SN2-like substitution. We have 2 carbons that are attached to bromine that are going to be having electron density pulled away from them, so a big partial positive. We have a great nucleophile here with the bromide ion. And so you're going to get a backside attack. So if the bromine is coming out towards us, the bromide ion is going to come from the back, and it's going to open up that bond. And we're going to be left with the bromine that was there first coming towards us, and the bromine that added second that had that backside attack, right? And is going to be adding from the other side. And so that's why we get this anti-addition. And this is a mechanism that you should be familiar with and know. I would expect you to know that this goes by way of a bromonium ion intermediate. So not a carbocation like other reactions we've seen, but specifically this cool little 3-membered ring bromonium ion intermediate. Now, there is well, actually not in this case. I'm thinking of the next reaction, so let me not get ahead of myself. We want to make sure, just to reiterate, we have anti-addition. We have this SN2 process in that last step, right? It is a nucleophilic attack and loss of a leaving group happening in one concerted step, just like we saw in chapter 7 when we talked about SN2 mechanisms. It is stereospecific. Okay, yes. Again, I'm only going to ask you about stereochemistry on rings. So I will not make you figure out when it's an open chain, if you turn it, whether or not it's a meso compound. I won't do this with you guys. Now, what's interesting here is solvent choice makes a big difference. When you see this reaction, it will often have Br2 or Cl2. And sometimes, not always, but sometimes you might see a solvent under the arrow. If you see something like CH2Cl2, that's dichloromethane. You guys have used it in lab. It is a non-reactive aprotic solvent. It is just there to dissolve everything. It is not going to interact. But if you switch that solvent with a protic solvent, you get something called Halohydrin formation. So now we're going to be adding a halogen and an OH. Right? So we're going to take our carbon-carbon double bond. We're going to add X2, but now we're going to put it in water. So we're going to add water instead of an inert solvent, or just not even mentioning the solvent. And on one side, we'll get an OH. On the other side, we'll get a halogen. It goes by a very similar mechanism. So the stereochemistry is still anti, but we are going to have to think about the regiochemistry now. If we have an asymmetric double bond, we are going to have to take that into account. So let's start off just looking at this mechanism. If you have already, and we're going to do this mechanism twice because we're going to do it on this symmetric double bond first. This step is exactly the same, right? We form, when we have bromine around, and I'm just using bromine, chlorine would work the same. You are going to make a little bromonium ion, just like we did in the last reaction. You have bromide around, but what is going to happen to bromide in water? Bromide is going to be solvated, right? Water molecules are going to surround it. And if water is the solvent, that means we have a lot more water than our reactants usually, right? You usually have more solvent molecules than solute. So water is also able to act as a nucleophile, and you have more of it around. So once you form that bromonium ion, just statistically, we're more likely to bump into water first, whereas the bromide ion is going to have left over on, stage right, and immediately be interacting with all the protons in the little water molecules. So water is actually going to do the backside attack, open up. There's no reason I chose the top carbon versus the bottom carbon on this one. Water came in from the back. Now, we don't want protons to just disappear without showing why. So it still has a proton on it, and the bromine is coming towards us. So oftentimes when water acts as our nucleophile, we do have to have one final proton transfer step. So in this case, and they show you here, right, another water molecule is just going to act as our base. We don't have any strong bases around, so water can do this for us. And that is how we get our final Halohydrin, right? It's got an OH group, that's the hydrin, the hydroxy group. Our halo group, the bromine. Right, so it's the same first step. It's really the same process as the halogenation. It's just water acts as our nucleophile, and we have a proton transfer at the end. And then we could put plus En because we would make both stereoisomers. But what happens here if we have an asymmetric double bond? Which side does the bromine, in fact, let's switch it up. Let's say we're going to use chlorine. Which side does the chlorine go to, and which side does the OH go to? We know they'll be on opposite sides of each other because it's anti-addition. So if the methyl is coming towards us, something will be going away, and then whatever's on this side will also be coming towards us. Well, it's important for us to recognize that the OH will go to the more substituted side. The halogen will go to the less substituted side. Why does this happen? So the OH would be up here and the chlorine would be down here. If we think about the intermediate, so I'm just going to draw the chloronium ion. So in this case, let's say the chlorine added to the front, right? The same way we'd make a bromonium ion, we can make a chloronium ion. Sorry, I keep tilting my iPad. And there would still be a methyl group here. So you would think, well, the water would want to add to the less substituted side, but it doesn't. It actually adds to the more substituted side. And the reason for that has to do with the transition state. As one bond breaks and the next bond forms, it leaves a partial positive on this carbon right here, the one where the bonds are shifting. And what's going to be a more stable partial positive? Well, the more substituted carbon. And so it's about that transition state energy. This right here, when this alcohol is attacking the water is attacking the carbon and the halonium ion is opening. This transition state between halonium ion and this intermediate, it's a lower energy if it attacks on that side. So it will attack that side more rapidly. So our major product pushes that chlorine over. So it's still coming towards us. The OH added, well, and it'll still have two hydrogens. We got to do a proton transfer. We'll add from the back, and it will push that methyl group forward. Then we can do our proton transfer. Water comes in, deprotonates, and we get our final product. Methyl group towards us, OH away, Cl towards us, plus the enantiomer. Right? The chlorine and the methyl group could both be dashed and the OH could be coming towards us. So there's an extra component when there's water. You have to know the stereochemistry is that it's anti. The OH and the X go on opposite sides. And you have to know that the OH adds to the more substituted side if you're going to predict the correct product. Right? Oh, and there's a picture. So this is the picture to help us try to understand why the water adds to the more substituted side. It's that partial positive that you get right there in the transition state that is stabilized by the additional R groups. All right. We have one more video where we are going to cover a couple more reactions and then a final part on multi-step synthesis. And that will be all of chapter 8. See you.